Greetings, everybody. This is Timur. Thank you for your interest in exabyte-io. Today, we'll be speaking about getting started with the platform. And before we start with this webinar, a couple of important notes. The goal of this webinar is to help users understand the main concepts behind the platform. It is the first webinar in the monthly recurring series of two. First Friday, we speak about getting started. Third Friday, we speak about advanced topics. Every participant today should be a registered platform user. And every participant will receive this presentation in a PDF format, so there is no need to take notes. The presentation contains links to documentation pages that cover the corresponding topics. And there will be a recording of this webinar also shared with all participants. If at any point in time you have questions about the content of this webinar or any other platform-related questions, please feel free to use Zoom chat or Q&A functionality to ask these questions. Here is the agenda for today. We will go through the platform capabilities first, and then we'll cover the core parts, what is under the hood, user interface components, actions, accounts, and service levels. And then we will go in more details through the actions that users can perform on the platform entities, materials, workflows, jobs, and such. Let's start with the platform overview. As we transition from the science driven by the three paradigms, like empirical science, theoretical science, and computational science, as we transition from just these three to the data-driven science, we have the need to have different data-driven, data-centric tools. And the reason why it's important is because the more information we accumulate, the more we can learn from this information using artificial intelligence and machine learning. And this is a fundamentally different approach than what people used to from the 20th century or 1990s or the early 2000s. And in order to implement this approach, we believe that we have to start with the cloud as the focal point where multiple different kinds of users can interact with each other and collaborate. That includes the computational scientists, the experimental scientists, data scientists, and their management IT forces as well. And of course, we have to support a vast array of simulation tools. And all these simulation tools have to feed data into a central repository in order to be able to run the machine learning on this data. And it all has to be secure so that no intellectual property leakage is possible. How do we go about implementing such a platform? We start with a set of open source components that together form the foundation for a fair R&D ecosystem. And FAIR stands for findable, accessible, interoperable, reusable. And we define three main entities here, which are extractors, standards, and applications. The data standards are the fundamental building block, and they pertain specifically to materials, which is material structures, simulation workflows, calculation jobs, and material properties. And these data structures are implemented in an object-oriented extendable way so that we can cover different kinds of material types, simulation types, and do that in an easy-to-use and a modular way. This repository that contains JSON schema is available on GitHub. It's open source and it's constantly being updated. Extractors are provided to help convert the data from any other existing sources, like simulation engines that we support today, into this format that we call SE, exabyte source of schemas and examples. We also have an example for an extractor provided on GitHub as another open source repository. And finally, the applications here allow users to utilize the data formats to create and edit materials information. We have an example application that implements solid-state materials design capabilities, as well available as a GitHub repository. Open source components then are used to build the publicly accessible online platform at platform.exabyte.io. These components can be licensed and further deployed in a private cloud scenario too for the enterprises that would like to do that. We start with computational material scientists as the most well-known use case to us. However, adding the data scientist and experimental scientist is also possible. And the final external components list that completes the picture of the Exabyte platform includes things like in-house computational hardware, in-house laboratory equipment, and data platform. So altogether, this is how the exabyte.io digital materials R&D ecosystem looks like. Now, there are multiple steps involved in the digital materials R&D, and among those we can list 7, starting from designing material structures, designing the modeling workflows and logic included inside, provisioning the high-performance computing infrastructure, controlling and asserting the completion of these calculations, collecting the data, building data analytics, and feeding experimental validation. And the Exabyte platform today supports 1 through 6. Here's an example picture of an account in the platform that demonstrates how we present the entities that we just discussed: materials, workflows, jobs, and we present the people that can collaborate within this account. So we can see that there are 4 people and they all can create and edit the entities. So when they create and edit the entities, they can see each other's work and they can collaborate and leave notes and make sure that this work is performed efficiently in a digital domain. So here's an example of how users can create new materials. This could be either semiconductor interfaces, like I'm showing it here, or this could be chemical reaction paths. And as we create the structures, we can also save them in a database in a well-organized and shareable way. For the chemical reaction capabilities, we group together multiple different structures into material sets so that we can see how the atoms change, the atomic positions change during the chemical reaction, as we can see it here. This is specifically useful for matched elastic band calculations, for example, to get the transition states. And then once we have the structures, we can set the simulation workflows and its computational parameters to prepare a simulation. And we have a set of simulation workflows that are shared among all the users of the platform today, of which we have over 1,200 as of right now. So there's a vast repository of knowledge about the simulation workflows and the properties that they produce. And these workflows can be assigned to a particular material and combined together with the computational parameters. They correspond to a simulation. And then we can execute the simulation. We can submit it to the computational infrastructure, which is also provided on demand here through as a service. And at the end, when the calculation is complete, we extract the data points in the form of a graph or a number. Okay, so that's the basic usage scenario. For people who are, this is an example property for the matched elastic band calculation that demonstrates the reaction profile. For people who prefer programmatic tools like Python, we also have the capability to create and edit the entities starting from Python. So here's an example where we import materials and then set up and run calculations for these materials, then wait for them to complete. And at the end, when the calculation is done, we extract the data from this calculation. like the material IDs, material structural information, crystal lattice and its parameters. And we also extract the final results. For example, there's pressure, there's direct band gap, indirect band gap, and things like that. Okay. And for users who are familiar with Jupyter, they can also start and use the Jupyter environment as part of the exabyte infrastructure. Here is a quick example of how Jupyter environment can be used to communicate with our RESTful API. So by providing the account ID and authentication token, we can communicate with the RESTful API, and we can extract the list of all materials, for example, that contain silicon inside its formula. The list is presented to us in JSON. All right, so this is 1 through 6 as the platform capabilities. Excuse me. Here are the applications that we support today. We have a set of modeling applications that we support on the command line level, on the remote desktop level, and inside the main user interface. There are also analysis tools that help us visualize the information and extract useful insights. And of course, we support Python and shell scripting at the infrastructure level, as well as the web interface. Some example applications that are available through the command line interface include these. And for users that are familiar with batch scripting and resource managers like PBS or Slurm, this can be used on a platform as well. And here is a quick example. This is how we can create a batch script by navigating to the platform, clicking terminal, opening the right-hand sidebar first, and then clicking terminal, and then editing a batch script to submit the calculation, monitoring it, and extracting the result in the end, right? So that's the familiar workflow to computational material sciences today. So here is the midway summary of what I just explained. exabyte.io is a comprehensive ecosystem for materials and chemical R&D with the goal of transitioning today's siloed or isolated approach to a fair, findable, accessible, and interoperable infrastructure ready for the data-driven science era. The goal of the platform is to supercharge computational sciences by providing a dedicated environment to organize and accelerate their work and connect computational material science with data science. The platform can be accessed on multiple levels: infrastructure for computational only, programmatic level, RESTful API, and the web interface. Now let's proceed to speak more about the core parts of the platform. What is under the hood? We'll see that the parts of the ecosystem that I highlighted in the diagram earlier, they are available on our GitHub page. So if you look at the GitHub page of exabyte.io, you will see there SE, which is where we store the standards. Then you can see exaparser, which is an example extractor. And you can see the applications, one of which is materials designer. There are also examples that contain Jupyter Notebook templates for working with the RESTful API. Users can clone them and run them on their computer. We identify a set of entities such as material, simulation of workflow, and calculation job. And you can see that each of them have properties that can be associated with them. So material has things like lattice, crystal basis, right? For example, and some of these properties are also produced by simulation. So the energy that this material would have, or things like hardness or thermal conductivity, the properties that require a simulation to evaluate, this would be one of them. And then depending on the workflow, each of these properties also have a precision associated with it. And We separate these entities on purpose to improve modularity and to be able to cover multiple different model and material types. Together, when we put the workflow, compute parameters, and material description, we get a job. And this job is then sent to the computational platform to extract the properties as shown here. The data structures are based on JavaScript object notation format, and we use JSON schemas as a way to organize the data. Again, this is fully open and available on GitHub and has implementations for density functional theory. It can also be used as a standalone package for Python and JavaScript applications on the web. Here is an example for a material schema on the left. It contains things like crystal basis and crystal lattice. And here is how an example material that adheres to the schema looks like. This is silicon. We have its bases with coordinates and elements and additional properties inside this data structure. Why it's important to understand the standards? It is important to understand the standards because we have to sometimes go beyond the capabilities that the user interface provides. And dealing with the data in a well-organized fashion makes it much easier to extract the necessary information using programmatic needs. And as we go further and accumulate more and more data over time, we have to understand that structure also to build any kind of artificial intelligence and data analytics upon this data. So again, a quick summary: every entity user encounters inside the platform is defined inside the exabyte data convention, or ESI, as we call it. The definitions are meant as a unified format to incorporate data from multiple different material types, modeling approaches. And the platform provides a user interface to work with these entities. And the entities can be also accessed automatically in alternative access scenarios. We encourage users' contributions. And here is an example pull request inside Materials Designer that was open to introduce additional functionality. So if you have additional functionality that you'd like to introduce, we can do that in an open source collaboration online. Let's speak a little bit about the user interface now. And here are the basic components of the user interface. On the left, we have the left-hand sidebar. On the right, we have the right-hand sidebar. At the top, we have the header. And there is a footer at the bottom and the support widget. So the most important one for the people who are just starting on the platform is the support widget. And here, how it looks like when we click on the button. What we can do here is to provide our name, our email address, and explain the problem that we're facing. And we strongly encourage with every single support ticket to provide additional information, like it's a screenshot, ideally a screencast that shows the video of where you're clicking and the problem that you're facing, because that helps us tremendously to understand the problem that you're facing. There is also another chat that's available to the users before they are logged into the platform. And here you can, in general, we discourage accessing the support team through this widget. But in some cases, if you cannot log in, for example, that's the way to go. Okay, so me in this chat for the users who are just considering the platform to help them register. But if you can't access the platform, you would send us a ping through this chat. So let's look now at the left-hand sidebar. To open it, we have to click on the top left corner. And the left-hand sidebar allows us to get to the entities that belong to our account, such as projects, jobs, materials, workflows, and such. And through the right-hand sidebar, we can open it by clicking on our account name in the top right corner. Through the right-hand sidebar, we can access additional payment options, account preferences, and remote connection methods. There are also entities-related interface components, and we identified 3 types of them. explorer or a table, a list of components for exploring the entities inside the collection. Designer is an online development design environment for the creation and editing of one or more entities. And a viewer, which is a dedicated page allowing to visualize one or more entities and make small adjustments to edit metadata for these entities, for example. So here is how an entity explorer looks like for materials. So this is the materials explorer. We can see a list of entities in the table with a table header and a set of actions. The actions available for multiple entities are listed at the top, and we call them tools. And the actions that pertain to each entity individually can be opened here by clicking on the entity and opening its corresponding drop-down. We can also search and filter the entities in the table by using the search capability, the search filter field. The entity designer is a component where we can create new entities or significantly modify existing ones. And here is an example materials design. It also has a header menu at the top, a list of items on the left, crystallographic data panel, and 3D interactive crystal viewer in the middle. And materials designer that we use in the platform, again, is a standalone open source JavaScript application. So if you'd like to add additional functionality, we can do that online together. And here is how the materials viewer looks like. We can see the materials parameters, its structural information, as well as metadata, things like its name and its tags. And we can edit only the metadata through the entity viewer. Now let's talk a little bit about the accounts and sharing. Accounts own and perform actions on entities. So accounts own and can edit materials, workflows, and job. Accounts define the different ways of how users can interact with the platform. So I can have multiple accounts that I am a member of. And through these different accounts, I can produce entities that are owned by this specific accounts. There are organizational or team accounts and personal accounts. Personal accounts have only one member, the person themselves. And organizational or team accounts have teams that have different permissions. So they can read and edit the corresponding entities. Account members have shared access to entities as set by the account administrators. We also have the concept of entity collection and the corresponding entity banks. Entities are by default collected inside the platform in a way that each account has their independent entities separately. So for example, if there are two accounts and each of them owns a particular material, let's say there are three entries in the account on collection for the same material. We store one unique entity that corresponds to this material inside the materials bank. And when the private data option is enabled for this account, no other account can access the entity inside the materials bank. And when the private data option is not enabled, all other accounts can see the data that resides in materials bank that is produced by account X. We did that on purpose. The account-owned collection is always private, and then the bank entities are those that can be shared within between different accounts depending on the service level. We recommend using this option to import from the bank for workflows. And this is how the bank can be opened directly from the Explorer menus, Explorer action menu. And for the people who are just starting with the platform, we recommend using entities produced by the curator's account. And those are curated by the platform administrators, so they usually have good quality. Now let's speak a little bit about the service levels that I briefly mentioned. Service levels define the features that are available to accounts. And there we have 4 different service levels, starting from free, which is the default service level when users create new accounts, and going to the enterprise, which is a feature, the most feature-rich service level that we support today. The features that define the service levels could be things like the availability of private data that I just described, the amount of disk space included, the number of account members, the support severity, how quickly you reply, the limits on the number of entities, the availability of command line access, and more. So now let's summarize what I just told you about the core components, the under the hood components. The data standards that define the entities, the concepts that you work with inside the platform are defined as a unified format. And we mean this unified format as a format that can be extended by the community to add additional material types and modeling approaches. The platform provides a user interface to work with the entities and provides additional alternative access options. The accounts can perform those actions on the entities in a shared access way, allowing users to collaborate. And features available to accounts are defined by their current service levels from free to enterprise. Now, let's see if we have any questions as of this moment. I don't see any questions as of right now, so let's proceed to speak about the entities more in details. So let's start with materials. Initially, when you deal with materials, likely you need to upload some materials information about the materials that you're already working with, the structures that you already have residing on your local drive. And here's how it can be done. We can click on the upload button in the top, I click select items, select multiple files from disk, click open, and now we are presented with the intermediate dialog where we can verify the content of these files if necessary. And useful feature, we can assign metadata to one or more entries in this preliminary dialog. Here's what I'm doing there. I'm listing 2 tags separated by comma. And when I'm happy with this list, I can import all the items from the list. I can click upload again, and all these 3 items now will correspond to materials inside my account collection. As we can see here in the top, we have these 3 items, and one of them also has the tags propagated. Another option would be to import material information from an online database, and today we support the materials project. So we can click on the import button and search for a material by its formula, and select the entry and click import. After a little while, this entity is imported. We can close the dialog, and we can see this entity at the top. And we can make sure this indeed is the entity that we want. The third option is to copy the entry for the material from materials bank. So as we get more and more users to work on a platform, the likelihood of someone working with a material of your choice is increasing. So we can open the left-hand sidebar, click bank and materials, and then search for the desired material inside materials bank. And then select this entry and click copy. So this way we'll have a copy of the bank material inside our account collection. Okay, like we see it in the top. There is also a direct option to navigate to the bank from the workflows and materials explorer. In some cases, the default filtering functionality available here in top is not enough, and we would like to filter materials by using some more advanced search criteria. And that can be done by clicking on the advanced search tool at the top, and then constructing a query with multiple and or conditions. So here I'm constructing a query that contains a formula that has the formula for materials that have formula that contains aluminum. And then the unit cell volume that is less than 80 angstrom cubed. And the entry that also contains tags with high pressure string in them. And as you can see, there is only one entry after I run this query. And when I reset it, I'm back to the full list of materials. Now, when I'd like to open the materials designer, I can do that by clicking on the blue plus button in the materials explorer. And here is how the materials designer looks like. We briefly spoke about it. It's a header with menu items at the top, the list of items that we work with in the current session on the left, crystallographic data panel in the middle, and the 3D interactive viewer on the right. And I'm just going to demonstrate some very basic usage example where we import a material from our account collection. So materials designer session, we can work with materials collection only. So we already have to have materials uploaded or imported or copied from bank. And then we can select them during the materials designer session. So here I'm using the import option menu at the top. And I'm narrowing down the list of materials, searching my collection by a tag, aluminum in this case. And then I select it, and here I can see it. And I can remove the default material, which was present there from the beginning. So the materials designer option. The materials designer session opens with default material silicon, as you see in this case. I don't need it, so I can remove it from the session. It is still going to be present in the database, but I just remove it from this materials designer session because I don't need it. And then I concentrate on working with aluminum nitride, the material that I just imported. Okay, so this is a basic usage scenario. We can cover more advanced cases in an advanced topics webinar. And now let's go forward and move on to workflows. Just like with materials, we can copy workflows from the workflows bank. And some people find this option very helpful. So we can search by the property that is extracted inside this workflow, like band structure. And then we can copy the workflow by clicking the copy option at the top. And then we can find it in the list of our workflows. We suggest using workflows that are created by curators. You can extend the number of fields, so you can add additional field, which shows the creator of the workflow. And we recommend using workflows created by curators account, because they're higher quality usually, and we test them frequently. Now, in order to understand how we can build a workflow from scratch, we have to understand the inner structure of the workflows. And those consist of subworkflows and units. Subworkflows is a set of, subworkflows are sets of distinct units, primitive calculations. Combined together in a flowchart, you can think about it as a flowchart as an algorithm, or a set of logical components. And each subworkflow must be specific to a single simulation engine, for example, VASP. And each subworkflow contains a single model, a single method, for example, supercontrol. The concept is introduced for modularity to be able to reuse the commonly deployed logic. And unit is the elementary calculation inside the workflow. It is executed in a certain succession based on the logic. We have different types of units, such as execution unit that can run simulations with quantum espresso or WASP, for example. Assignment units where we assign variables, condition units when we can split the logic inside the workflow. Execution units have executables such as pw.x for quantum espresso, and flavors such as pw_scf for self-consistent field calculations. So these are template input files that we hold inside the units for commonly used use cases like self-consistent field calculations, non-self-consistent field calculations, things like phonon calculations. For every specific kind of unit calculation, we can think about a flavor and the corresponding template. Again, we made this distinction on purpose to make the process of the creation of the workflows and then the process of the deployment more modular and reusable. And here is how the workflow designer looks like in the platform. We have the header menu at the top and the list of items on the left, and this Subworkflow editor on the right. Here is a quick demonstration of how we can add and delete a Subworkflow. We click on the plus button and click apply to append a Subworkflow. And we can switch to it by using the arrows. And then we can delete it by clicking the minus button. You can see the currently active Subworkflow is highlighted in gray. So we can switch between one to the other. Now, to be able to edit the units, we have to use the Subworkflow editor and navigate to the units flowchart. The units flowchart demonstrates the logic that is involved inside this workflow. And we can see that the currently active unit is highlighted in gray. The type of unit is shown in the bottom left corner. And we can click on the unit to open its detailed view. And the current representation is rudimentary. So the flowchart on the left really is going to look like this in the platform today. You can see there are execution units again, a condition unit, and an assignment unit. When we open the units, we will see the section that pertains to the application, in case it's an execution unit. The properties that are extracted, the monitors that are extracted during the calculation, properties are extracted at the end of the calculation, monitors are extracted during the calculation. We have the information about which units will come next. And at the bottom, we have the input templates. So here, what's important to understand is that the input templates, they contain variables. The variables that are substituted based on the materials information provided to the current workflow designer session. And this material information comes from the materials that we have imported and stored inside our account collection. By default, the workflow designer session has the default material as the entity that we can prototype the workflows with. And we can see it in here in the preview tab. So if you click on the preview tab, the default material will be available there. In the case when we have more than one material, you can cycle through multiple entities here to make sure that the preview works for each one of them. The preview is the first render that happens on the web. Some of the variables you can see are still not resolved. We use Trinja, and you can see that some of the variables are still left even after we preview the initial input file. And that happens because really these variables are not necessary for the user to know about, right? There is no need for the users to understand which job working directory we are going to substitute this variable for. That is done during the second render, which happens on the infrastructure side. And this second time render on the infrastructure side also enables logic that is involved inside things like the convergence workflow that I just demonstrated. Okay, now let's continue to speak about the jobs. So once we have a material and a workflow, we can proceed to run simulations for this material and workflow. But before we start, we need to make sure that we indeed have this material and workflow, and our account has enough balance to perform the calculation. Our account has enough disk space, disk quota, to perform this calculation. Then we can navigate to the desired project. This is how we organize the jobs. Jobs are collected inside projects. Or if we would like to use the default project, we can click on the create job in the left-hand sidebar. If we do that, we are redirected to the job designer. And the job designer contains 4 main components: the header menu at the top with drop-down and items, the action items here, and materials tab, workflows tab, and compute tab. So step number 1, while we design a job, we need to select its materials. We can do that by clicking the header and selecting select materials option, and then choosing 1 or more materials. So here I'm selecting 6 entries from the materials collection that I own. And you can see here that all these 6 entries are now added into the materials tab. I can cycle through them. And you can also see that the job name now has the formula variable inside it, which will be substituted upon the creation of the jobs with the material formula. So you can see we have multiple different materials in this session, and multiple different jobs will be created according to this naming convention. The second step is to select the workflow, and it can be done also by clicking in the right-hand sidebar. Yeah, sorry, in the header and selecting the corresponding option, and then choosing a single workflow of interest from the workflows collection. Right, so here I select the funnel density of states, and scroll back to the bottom of the page. You'll see that indeed it contains the desired logic. The step number 3 is to set the computational parameters, and this include things like the time limit. On purpose, we limit the maximum amount of time that the calculation can run for. And by default, it is 1 hour. Please pay attention to this setting, because sometimes we see users get confused about why the calculation had stopped. And that's because we don't want you to run out of credits and run overly long calculations. So this parameter has to be adjusted to be able to run longer simulations. Now, the computational parameters like the cluster, where the calculation is executed, the resource management queue, the number of cores and computational nodes, as well as some advanced options can be also set here at the bottom. And I can also select to receive notifications to my email address at certain moments for this job, when it started, aborted, when it's ended. When I am through the first 3 steps, I can click the Save button at the top in the header to save the job. A couple of notes about the job creation. Workflows cannot be modified during the job creation. We do that on purpose to simplify the user interface components and to assert the data consistency. Users should modify and edit the workflows first instead, and then select the modified workflow during the job creation. So a common usage pattern is to create a copy of the workflow if you need to modify it, and then adjust its metadata, adjust its name, adjust its logic, and then reuse that copy during the job creation. There is a way to modify the content of the input file, override the requirement here, and directly modify the content of the preview. But we suggest to avoid it, again, to retain the consistency of the data. Multiple materials can be selected for high throughput job creation, or for multi-material, consider NAB or chemical reactions calculations for that. Jobs can also span other jobs and wait for their execution. So each job has the capability of launching other jobs and then waiting for them to complete. But that's a topic for a separate webinar. Now, when we have created the job, it's initially will be in the pre-submission status, shown with the this blue icon, light blue icon, and status with a P in it. If we want to run the job, we can select it in the list and select the run option. So we change the status to submitted and dark blue. In a little while, we receive the information about when the job is going to start and how long it has been running for. So here we see that it was in the queue for 1 second. And that's because we submitted it into the debug queue, which has a very quick turnaround. And now it's been running for 8 seconds already, and it's now in the active status shown in orange color. When we open the active job, we can see that now it contains additional entries. So when we open the page, we see that there are, in addition to the materials, workflow, and compute tabs, we have the results tab and the files tab. And we can see that the units of which the first one is currently active. Excuse me. This is a way to monitor the job. We can click on this unit and we can see its output file posted to the application in the real time. And we can also monitor the convergence graph, which is updated in the real time too. So when the calculation is done for the first unit, it is shown in green, and the second one is shown as active. So when the calculation itself is done, when the job is complete, its status turns to finished, and the color turns to green. So we can open it and explore the results tab. You can see the results arranged by unit. And we can see the input files. We can preview the textual files or download the binary files to disk, for example, from this web page. Okay, so that's how we create and edit the jobs using the materials and workflow information from before. This concludes the content that I had for the webinar today. Let's see if we have any questions. No questions as of right now. Okay, so if you do have any questions, you can always send them to me at timur@exabyte.io. And we'll be running the next webinar in 2 weeks, and we'll be speaking about the advanced topics, and I hope to see you there. In the meantime, please stay safe, and thank you for your attention. See you soon.